Hello there, everyone. Welcome to our senior design demo. Our project was on analog to digital converter reliability testing. The team members were Herschel Millman, Katrina Harmon, Taylor Swatson, and me, Eric Tepper. Now, before we start discussing why our project of analog to digital reliability testing is extremely important, we must first go over an overview of what an ADC is, or as I like to call it, an analog to digital converter. Now, in electronics, an analog to digital converter is a system that converts an analog signal, such as a light pulse picked up by a semiconductor into a digital signal. Now, in layman's terms, we can understand this as a device that converts a signal that we can interpret to a signal that a computer can interpret. Now, with that said, it can now easily be understood why these devices are extremely important and why we must know when they won't fail. For instance, if we were to send up a satellite into space that had a sensor that calibrated its thrusters and they were off a little bit, it could cause a catastrophic failure, which could lead to billions of dollars lost and possibly lost lives if it's used for guidance systems. So, for these reasons, our project is extremely important.
Thank you, Eric. And now I'm going to talk about why we decided to use daughter boards. As Eric previously mentioned, we are testing 3 different ADCs from 3 different manufacturers. Each of the ADC comes with an evaluation module that includes a PCB board, the ADC, resistors, capacitors, and associated ICs that are all rated for the same temperature environment. Since these parts are all rated for the same environment, there would be uncertainty as to where the error would be introduced in the signal. So our solution was to design and print daughter cards that will isolate the ADC for testing. This way, only the ADC and the decoupling capacitors are exposed to the hostile environment inside of the test chamber, while the evaluation module is outside of the test chamber at ambient temperature. The daughter board design process included the following steps. First, we used a PCB software design tool called Eagle to lay out the schematics for a daughter board. The parts included the ADC, the decoupling capacitors, and the pin connector. The next step transformed the schematic into a 2-layer PCB board layout. The bottom layer is the ground plane, and the top layer has the ADC, the pin connector, and the capacitors. These were designed and printed, but not without a few challenges that we overcame. For example, not all of the ADC parts had readily available CAD libraries to use. Also, the Maxim integrated part did not have a footprint that was available, and this had to be made by hand by Taylor. The part itself has very small dimensions, so the widths needed to be adjusted, especially for this part. Also, each ADC part is a different size, so therefore all of the PCB daughter boards are not the same dimensions either. There are a different number of pin connections for each ADC, which means there's 3 separate pin connectors that needed to be ordered, as well as 3 different ribbon cable types. Lastly, the analog devices daughter board required the use of 2 different ground planes for both analog and digital ground plane, while the Maxim integrated and Texas Instruments daughter board only used 1 ground plane. After making all the necessary adjustments with the tools that we had available, we successfully designed and printed 3 daughter boards. And now Taylor will talk about the data collection process.
During the data collection process, we did run into a few issues. The first was that we had a third party do some modifications to the evaluation modules so that we were able to hook the ribbon cable into them. And several of the solder joints were not done correctly. They weren't hooked into the right places. So that took some debugging and we had to resolder some of those ourselves. After that, we were supposed to have access to a logic analyzer in order to analyze the TI board. It does not have a USB interface like the other 2 boards, so we needed a logic analyzer in order to be able to pick up measurements from it. Since we did not have access to it, we were not able to collect data from the TI board. We were able to functionally verify it by using a probe in the oscilloscope, but we weren't able to actually collect data from it. After that, the Maximum integrated board has a USB interface, but we ran into some issues with it. It was not functioning as intended. So we encountered that issue. And the last but primary issue that we ran into was that by using the daughter board setup and connecting in the ribbon cable, we had actually introduced quite a bit of noise into our setup. So a lot of our data isn't completely accurate, as there was a lot of extra noise introduced as the signal was first going over and then being transferred back to the evaluation module that was not part of the original design. Up next, Herschel will tell you a little bit more about the analysis phase of our project and our results.
Thank you, Taylor. In order to characterize our converters, we produced histograms of the output codes when the ADCs were given sinusoidal inputs. We performed these tests in many different environments, but the only significant results occurred in our temperature tests. The cold histogram was the closest of the 3 to the ideal bathtub shape that was expected. The room temperature histogram had a lot of noise in the middle, as well as distributed throughout the histogram. The hot histogram had the highest spike in the middle, indicating that the most non-ideal behavior occurred at this high temperature. Heat causes non-ideal behavior in analog to digital converters. Because of this, it is crucial that these converters be designed in such a way that they are not overly sensitive to unusually high or low temperatures. More robust setups are required for accurate testing of sensitive circuitry. In order to more accurately characterize the effects of hostile environments on analog to digital converters, it is necessary to perform a control test first to gain a baseline for comparison. It is also necessary to ensure that the circuits being used to test do not introduce any non-ideal effects of their own, such as voltage drops or heightened inductances. We had a great time working on our capstone project this semester. Thank you to everybody who provided us with guidance along the way, and thank you for watching this video.